We learned from quantum mechanics in Chapter 3 that electronic states are quantized. Yet when we look at the number of states versus energy, a continuous curve emerges. This curve, known as the density of states, is a widely used concept in solid-state physics that comes from quantum mechanics. We learned that one of the best ways to describe the electronic states in a band is through the linear combination of atomic orbitals. The lowest energy state is described by atomic orbitals with bonding interactions between each atom. We can describe that bonding wave function as a linear combination of atomic orbitals where, in the case of S states, each orbital has the same positive phase. The highest energy wave function in the band is also described as a linear combination of atomic orbitals, but in this case we have anti-bonding interaction between each atom, which is represented as alternating the sign of each neighboring wave function. Most of the wave functions in the band are between these two extremes and have both bonding and anti-bonding interaction between their atoms. Mathematically, these wave functions can be described as waves of atomic orbitals that we call Bloch wave functions. For example, the most bonding wave function is described as a summation of its atomic orbitals, where each atomic orbital has the same positive phase. We can write that phase as e to the I kr, where k equals 0, making e to the I kr equal to 1. For the most antibonding wave function, the phase alternates between +1 and -1, which we can write as e to the I pi over a times r, where r is the position of each atom and a is the distance between neighboring atoms. Thus, for the first atom, when r equals a, e to the pi I is -1. Remember that e to the I kr is cosine kr plus I sine kr. Then, when r equals 2a, we get e to the I times 2 pi, which is back to +1. Thus, we can also describe this wave function with a phase e to the I kr, where this time our wave vector is pi over a. For the wave functions in between, they can also be described using this Bloch wave function formalism, where e to the I kr has a wave vector somewhere in between 0 and pi over a. While the type of atomic orbital determines the average energy of this band from all these wave functions, the spreading between top and bottom of this band depends on this wave vector e to the I kr. The distribution of states, particularly from the bottom of the band, will look like free electron states, which were also described with such waveforms. We now want to consider the number of states or wave functions that would exist within the entire band. While there is only one possible wave function that is fully bonding or fully antibonding, there are many possibilities to have states in between. Even for a state with only one bond and the rest antibonds, there are many different places to put that one bond. Thus, we expect the distribution of states to be greater in the center of the band. Here, darker regions represent more states. Drawing this schematically, we would expect the number of states to increase continuously, reaching a peak somewhere in the middle of the band, and then also decreasing back to 0, top of the band. This schematic curve is known as the density of states, which we describe with a function g, which depends on energy E. This density of states function g is a density in two ways. G is the number of states per unit energy and also per unit volume of the sample. For example, g of E times some dE interval of energy describes the number of states or number of wave functions that exist in this energy interval per unit volume of the sample. If, for example, I wanted to know the total number of states up to a particular energy, then I would take the G of E times dE and sum that up over that energy range, which is an integration. Thus, graphically, the number of states is the area under this curve. Thus, we often think of filling the density of states curve up to a particular energy to tell us how many states exist up to that energy. Now, because the number of states is the integration of the density of states, if we take the energy derivative of both sides, we get simply that the density of states is the energy derivative of the number of states. We will use this expression to find density of states from number of states as a function of energy. Let's consider the solution to wave functions for electrons in a three-dimensional box that we solved in section 3.6. We saw that those wave functions can be described as waves that are very similar to free electron type waves, but these waves must fit within the size of the box. Here we will use a square box where each side has length L. We learned that the energy of these wave functions can be described as h squared over 8m L squared times an energy quantum number n squared, where n squared comes from the x, y, and z quantum numbers little n squared. Each possible configuration of integer quantum numbers for each of the three possible n quantum states helps describe the number of ways to get a particular energy quantum number, capital N squared. Thus, as we look at higher energies, we will see more possibilities or more number of states with the same energy. While at low energies, the distribution seems a bit random, as we go to higher energies, we see a pattern emerging, and this is the curve that we are going to be solving for. We can think of each quantum state as being described by a block in the three-dimensional space described by the quantum numbers n1, n2, and n3. In each block of volume 1, there is exactly only one state. The energy quantum number, given by the sum of the squares of the individual quantum numbers, describes a circle in the n1, n2 plane, or a sphere in the n1, n2, n3 volume. Thus, we know a state has an energy less than a particular value if it lies within this circle. We can also then estimate the number of states that exist with energies less than a particular value as the area of this circle. This should be particularly accurate for large energies or large n. Now, because the quantum numbers n can only have positive and not negative values, we're really only interested in half the circle for each dimension. In 3 dimensions, then, the number of states less than a particular energy is described by 1/8 the volume of this sphere, where the volume of a sphere is 4/3 pi r cubed, where r is our energy quantum number. Now, to find the density of states for a free electron, G of E, we will take the energy derivative of the number of states per unit volume. From the last slide, we've derived the number of electronic states up to a particular energy quantum number. That was 1/8 of the volume of this sphere, 4/3 pi quantum number cubed. And the volume of our sample is given by L cubed, the volume of our cube. Now, we mustn't forget that each of these wave functions can hold 2 electrons. So the number of electron states is 2 times the number of wave functions. We wish now to convert from a function of the quantum number n to actual energy E. We use this using the relationship between energy and our energy quantum number, where we solve for energy quantum number in terms of energy, moving the 8 massive electron over, taking the square root, and then we end up with H and L now at the bottom and the top. When we plug our quantum number into our number of electron states up here, we will cube it, which will give us an L cubed to cancel the volume term below. This gives us a pi over 3 from up here. The H cubed comes from cubing the H down here. Then 8 mass times energy to the 3/2 power, where the 3 comes from the cubing of the energy quantum number up here, and then the 1/2 power comes from the square root in the relationship between energy and the quantum number. Now, taking the energy derivative to get the density of states, we see that we will need to bring down a 3/2 and end up with a energy to the power of 1/2, whereas the effective mass will be at a power of 3/2. To recap, the free electron density of states is described by a function, g of E, where g typically is 0 at the bottom of a band and rises continuously. In 3 dimensions, this density of states function is described by the square root of energy, which on a plot like this looks like a parabola. The number of states per unit volume is given by the integration of g of E with respect to energy E, or the area within this curve. Because electrons fill up energy states from lowest energy first, and only 2 electrons can fit in each energy state, they tend to fill the density of states curve up the way water would fill up a bowl. This is why we draw our density of states curves often with density of states as the x-axis and energy as the y-axis, to think about a filling of our electronic states. Mathematically, then, we would describe the total number of electrons, n, similar to the way we describe the total number of electronic states up to a particular energy. The difference being only the probability function f, telling us whether a state is filled or unfilled. In the case of electrons at temperature 0, the states are filled up to the Fermi level. In the next section, we will discuss various distribution functions f.